Thank you. Hello, everyone. I'm Romain Allart. I'm a postdoc at the University of Montréal. I would like to thank a lot the organizers to give me this opportunity. So for those of you who don't know me, I'm not doing radial velocities. I'm doing exoplanet atmospheres. And today I will speak to you about the atmospheres of the most unique exoplanet or most unique planet, the Earth. So this thin layer of atmospheres is only what allows us to live on Earth and what protects us from the space environment, but it's also what disturbs all our ground-based observations. And because of the telluric absorption lines, we need to, for radial velocity, it was either the telluric lines were either masked or sometimes telluric corrected. And so we'll just show you a couple of telluric correction that was applied since 1986 with telluric stars as a reference. There is also other techniques about empirical methods using PCA-like technique. We also have model-based methods like MolecFit. We are starting to see also a combination of model and empirical methods as it is done for the EPRV pipeline in SPIRU and NIRPS. And finally, we also have data-driven post-processing techniques like wobbles or YARARA. However, none of these techniques can easily be applied in an automatic pipeline that can correct a single spectrum. And so it's what led us to develop a new automatic, simple telluric model for the ESPRESSO pipeline. And yeah, I also want to point out that there is another talk after mine and also a poster from Yui Kasagi on telluric correction. So this led us to publish this paper in 2022, which is called the Automatic Model-Based Telluric Correction for the ESPRESSO and Data Reduction Software, and what I will present to you today. To know more about ESPRESSO, you can see the talk of Christophe Lovis from yesterday. So here you have the Earth transmission spectrum on the top panel with the water and oxygen absorption bands in the spectral range of ESPRESSO. In the middle, you have the spectrum of Tau Ceti with ESPRESSO, and bottom, the spectrum of Proxima. You can see the gray bands here are the telluric regions that are excluded from the computation of the cross-correlation function to derive radial velocities. So you see that is quite a broad spectral range that you need that you are removing when you compute the radial velocities. So this the model that you developed is a single atmospheric layer radiative transfer model. So we just use the basic parameters of the iTrend database combined with the information on the local weather to produce the high resolution transmission spectrum, which is then convolved to the instrumental resolution at each pixel using an instrumental resolution map, as you can see on the bottom right. And we are performing a fit, and the two main parameters that you can play with to better represent your telluric model is the pressure of the atmosphere and the water content, so the depth of the line. So both pressure and water, precipitated water vapor, will play on the depth of the line and on the shape. Here I'm showing you a selection of water telluric lines in the spectral range of ESPRESSO, which are the strongest water lines. And you can see that the residuals are always close to the continuum level. And it is on these selected lines that you can perform a CCF of telluric to optimize the parameters of the model to better adjust the telluric correction. And here is an example of this telluric CCF of water for different spectral types, from A-type stars, F-type stars, G-type stars, K-type stars, M2 and M5. And you see that every time the residuals are within the continuum or the pseudo-continuum of the telluric CCF, which means that you are reaching our photon noise level. And as you can see also for Proxima and JG456, which are M-type stars, the continuum is a bit more contaminated by blended stellar lines, but we are still within the pseudo-continuum of the CCF. So this allows us to say that we have a good telluric correction, but now what is the impact of this telluric correction on the radial velocities produced by ESPRESSO? So to do this, we produced different CCF masks, including more or less the telluric lines. And you can see examples of different masks that we use, where in the wet part of ESPRESSO, we go from the current DRS mask to the ideal case, let's say. What I can tell you is that the best mask that we found out is still the third panel, which includes more wavelength range, but still excludes two orders. So let's go to the first stars that we studied, which is Tau Ceti. So I think it's the most famous G-type stars. And you can see here in blue, the actual CCF of Tau Ceti, so with no telluric correction. And in orange, the CCF produced with a telluric correction and with an updated mask. You can do the difference of these two data sets, and this is what you obtain. You see clear residuals with an amplitude of up to 72 centimeters per second. And we think that these are linked to microtellurics. And how we can prove this is by computing the CCF only on this specific spectral range, which is between 500 nanometers and 600 nanometers, where CCF telluric lengths are not masked by the default mask. And you can see that when you do the difference of the radial velocity with telluric correction and with no telluric corrections on the specific wavelength range, you see again the same residuals with an amplitude of up to 1.4 meters per second, clearly showing that radial velocities of Tau Ceti are impacted by microtelluric contamination. Here again is another way to show this impact, where you have the radial velocity, uncertainty induced by the microtellurics as function of the EPRV and color coded as the content of the water vapor content. Now we can do the same for Proxima, which is a very famous M5 type star. And what you can notice first is that in this spectral range, where you have microtellurics, there is no flux for Proxima. So you are not contaminated by microtellurics in case of M-type stars. However, you can see that most of the flux for Proxima comes in the red part of the spectrum, where most of the spectral range is masked due to the telluric contamination. So by applying our new mask that you can see here, we are able to gain a significant fraction of the spectral domain up to 25%. And so it leads us to more spectral lines, which lead us also to an improvement of the photon noise from 28 centimeters to 21 centimeters per second. This is a gain of 25% in photon noise, so improved radial velocity precisions, but it can also be seen as an improved exposure time, a shorter exposure time to have the same RV precisions, and so a better use of the telescope time. So based on this, we did a new analysis of the radial velocities with the telluric correction following the paper of João Faria 2022 with the discovery of Proxima D. So you can see here the period, semi-amplitude, and eccentricity for planet B on the top panel and planet D on the bottom panel. And when you compare the CCF without telluric correction and the CCF with telluric correction, and you can see that there is a clear improvement in the eccentricity and planetary mass of Proxima D, not B. And you also have a reduction of the RMS with the telluric correction. And these new parameters are in better agreement with the template matching used in João Faria papers. And so what we can expect is that when you combine the telluric corrected spectra with the template matching, we can even more improve these parameters. Now, this shows that for ESPRESSO, this telluric correction is working very well, and we can extend it to other molecules like oxygens, also to a more difficult spectral range, which is the near infrared. And because ESPRESSO and NIRPs are sharing the same data reduction software, we're also working on the implementation of this telluric correction for NIRPs. And you can see here an example of the telluric correction for water vapor on the top panel, oxygen lines on the bottom left, CO2 lines in the middle, and CH4 on the bottom right. And you can see the quality of the telluric correction for all these molecules that will be delivered through the DRS pipeline of NIRPs. And this is, we also, as mentioned by René Doyon yesterday, we also have a second pipeline, which is the EPRV pipeline from Spirou, which has a similar telluric correction approach with a complementary steps, and we are in very good agreement between the two results. So to summarize and to show you the perspective of the telluric correction, here we just developed a simple one-layer additive transfer model for automatic telluric correction. It is in good agreement with other tools available to the community that I described quickly at the beginning. The impact of microtellurics is non-negligible for G-type stars with ESPRESSO, and it has to be considered in the analysis. The gain in photon noise is also important for late-type stars like Proxima. So for the ongoing activities and what you can expect for the future, we have the adaptation to other molecules in instruments. So we not only in NIRPs, but we are also working with Xavier Dumusk on the telluric correction for ARPS and ARPS North, a spectrograph, because all these instruments share the same pipeline, so we can have the same process steps to deliver the data products. This Python code is also available in GitHub for ESPRESSO and NIRPs. I put here the link. And this is also, if you are using NIRPs, ISO will redirect you toward this Python code for now for the NIRPs telluric correction. And we're also working in Geneva, with colleagues in Geneva, to the implementation of ESPRESSO and NIRPs GRS pipeline to produce this data product automatically. And the applications to other science labs still need to be explored, but it will be coming in a few months. Thank you.
All right, we have time for one quick question, I think.
Hi, this looks very interesting, and maybe the answer to my question is hidden in point 2 of your summary there, but you're using a single layer model, and have you explored the performance difference between the single layer model and a more traditional, many layer, 100-layer model? And I mean, there's a computational gain by the single layer model, obviously, but I'm wondering, at the signal noise and resolution that we typically work with, are you able to get the same performance?
Yeah, a good question. So we tried different line profile also, and we did a comparison between, for example, MolecFit, which is a very powerful tool with which uses a multi-layer computation, and we have the residuals that we are seeing are quite comparable between MolecFit and our telluric correction. I would not say it is clear for all telluric lines, but I would say for most of the telluric lines, it is working very well, but also MolecFit cannot be applied in a automatic pipeline. So it's where we have a big gain because of the automatic processes that we are able to do on this telluric correction.
Great.